Hi everyone, welcome to Seismic Data Processing course. So in today's lecture we are continuing our lecture about the migration. So we have over and under migration. Migration depends on the velocity model used. If the velocity is not accurate, the image of the subsurface structure will be distorted. We have two types, over migrated and under migrated. Over migrated, the velocity used is higher than the actual subsurface velocity. The effect of that reflection are pulled too much inward, causing over-corrected and often inverted or collapsed structures. We have undermigrated. This is the velocity used is less than the actual subsurface velocity, and the effect reflections are not fully corrected, remaining too broad or arced. So in case of over-migrated, in case we have this actual migration, the velocity is 1000 miles per second. If you use a velocity is bigger than the 1000, you will have slightly collapse inward, and we have also higher over-migrated, and we have if you increase the velocity, you will have severe over-migrated with this 20% higher. And in case of under-migrated data, under-migrated, the actual migrated velocity we have, in case we're using 1000 miles per second, the migrated velocity is 8 miles per second. So you'll have curved wide diffraction here, and if you increase the velocity, you will have less diffraction and less diffraction until you back within migrated velocity 1000. You will have this figure within your seismic traces. Also, we have 2D and 3D migration. Within the 2D, you will have only the X and Y, and these events will collapse one to each other, but within the 3D, you will have these events separated. You have X and Y and Z, so you can see the difference easily with your data. So this is 2D seismic data. You can see this is the erosion. This is not showing discontinuity, but within the 3D, you can see this is one continuous reflections. Is not we don't have discontinuity or erosion happening here. The same, so you will have one continuous reflections, and here is showing you have discontinuity or erosion happening here. So 3D seismic allow you to see your data within a clear image. Also, we have time and depth migration. The time migration used when lateral velocity variation are mild or moderate. This example for the subsurface layers are relatively uniform laterally. The output sections is in two-way travel time, meaning reflections are positioned based on how long the seismic wave take to travel down and back up. This is work well for simple geology, but in case we have fault, dipping layers, or salt bodies, we use the depth migration, because depth migration is account for velocity variation in both vertical and horizontal direction. But with time migration, you will account the velocity per depth, only the vertical direction. With the depth migration, you will take the vertical and horizontal velocity with your account. So depth migration allow you to have more accurate image. It's not about the changing in units, it's about how the velocity R would change. So if you see now there is a velocity, if you use the depth in here, pre-stack depth migration, the reflection will be smooth transactions between the layers, and here the velocity contract, but with the time you will have different reflections not representing the actual depth. You will have shifting in time in here. So we also have pre and post stack migration. This is migration classification according to its position in the workflow. We have post stack migration and pre stack migration. This happen after the stacking, less time and low cost, and we have loss in data. But the pre stack you will have take a long time and high cost, no data losses. So pre stack migration is more accurate, and you'll have no losses in data. This is the workflow of post stack. After stacking, you will have the CMD, gather, common midpoint, and after we calculate the NMO, normal move out velocity, we correct, and then we use the stacking. So these we correct for within the stacking. We collect all the traces and we stack them within one individual stack, and then we use subsurface velocity model, and after that we do the migration. You will have post stack depth migration cube, This is to back all the geological subsurface layer to the true position. But in case we have a pre-stack, this is the common midpoint, and we do the NMO, normal move out correction velocity. But after that, you will take all the traces individually and filter them one by one, and then you calculate the subsurface velocity model. And we will do the migration. You will not do the migration for just all one trace. You will do the migration for all the traces, but the migration will be for all the traces individually. And then you will have this the pre-stack depth migrated cube. So this is in case of this boss stack and the pre-stack. This is the boss stack. You will see you have a diffraction here with your reflections, but in here at pre-stack it will show you will have very clear diffraction here. And also deeper in depth, you'll see you have more diffraction, but in case you have only one reflected in here. So the critical parameter, you have migration, aperture, and depth step side and stretches factor. This is the critical parameter. The method uses, we have Kirchhoff migration and Vignite difference and stalled migration, and the effect for each one. This is small aperture cause removal of a steep depth, and this is the optimum depth step size is the largest depth step with the minimum tolerable phase error. And for the last critical parameter, in case of you have a setting factor, this the large the vertical velocity gradient, the smallest the stretches factor needed to be. So this is all you need to know about this lecture. So thank you for watching, and see you in the next videos.